So I need to find V phase. I need to find the I phase, and I need to find the angle. Those are the three values I need. So now the impedance per phases, this is the Z impedance. So I have given Z equal to 10 ohm minus J10. So this is minus J10 and this is 10 ohm. This is one phase. It's 10 plus minus J10. If you change it to polar, it's going to be 14.14 and angle minus 45. Ohm. So the first thing we found here from this one, that theta is minus 45. Theta, if we're measuring the power in the load, it is the load angle, the impedance angle. Then the second thing, we have the voltage here between these 2 points. See, between A and B, so it's the line voltage. We have the line voltage given, 220. From here, I can find the phase voltage because this is a Y connected, so phase voltage is the line voltage divided by square root of 3. This is the relationship. So this gives me 220 divided by square root of 3. This gives me the phase, which is one of the things, the three things I need. The magnitude for this, 220 divided by square root of 3, I think it's about 116. No, 127. Volt. This is the second thing that I need. Now the third thing is I phase, which is I can use Ohm's law, V phase divided by Z. I can use the magnitudes only, so 127 divided by 14.14. That's the magnitude. I only need the magnitude. You could put the angles, but you're not gonna use them here. So 127 divided by 14.14, that is about 9, I think, ampere. So at the end, the reading because this is the part here, reading of each wattmeter which is omega 1 or omega 2 or P1, P2, P3. V phase, I phase, cosine the angle. Now we take the phase values because it's one phase. So 127 times 9 times cosine minus 45. And this should give me a number. You can calculate it. no, I got 808. Maybe right, maybe not. You can check the calculation. So this is the answer for this question. I believe there isn't the assignment questions like this question. It doesn't say draw or sketch the required connection, but it says find the reading of the watt meter. Now this is if you have 3 watt meters. If you have 2 watt meters, you're gonna use the other formulas for the 2 watt meters. Is this okay? Any questions? Quite very early in the morning. Okay, we're done here. We did this one. So I'm gonna stop sharing this and start a new share. So the lecture 10, the concept, it says the lecture power factor. So power factor improvement. So we're gonna improve the power factor. What does that mean? Increase it. So we know that power factor is between 0 and 1, or and it's either leading or lagging. So the maximum power factor is 1. This is perfect. Okay. This is the highest. It's between 0 and 1. Now 1 is called unity power factor. Sometimes when you hear unity power factor, it means just 1. Now power factor is actually real power divided by S. So when it's 1, which is the perfect power factor, means P equals to S. In this case, Q equals to 0, because we know that S is P squared plus Q squared equals to S squared, we can say. So if S equals P, Q is 0. So when we want to increase or improve the power factor, we are gonna try to make Q 0 or smaller. Okay, so small number, like doesn't have to be 0. An example. This is P. This is a Q. This is S. Okay. So to increase the power factor, we reduce this angle. So let's say that becomes like this. P, Q, and S. So what we did, we reduce Q. Once we reduce Q, we reduce S as well. We don't touch P. P is the real power. We don't want to reduce it, because if reduce the real power, the load is not going to work. So how can we now reduce Q? And what is the point? Why do we want to increase the power factor? Why we say it's 1 is a good power factor? Why it's not 0.5, 0.6, or 0.4? So here's a load. Let's just do single phase for now. This load has P equals to 80. Say just watt. Q equals to 60 volt ampere reactive. Then in this case, S equals to 100. P squared plus Q squared under the square root. Power factor equals to 0.8. Okay. Voltage is 50 volt. And this is the source that gives you 50 volt. Here's another load. P is 80. Q is 0. S is going to be 80. Power factor is 1. The voltage from the source doesn't change, 50. Now we know in a single phase S equals VI. So in the first load, this one here, S is 100, V is 50, I from here will equal to 2. So the current coming here is 2. Now for the second one, S is 80, voltage is 50, I in this case will be 80 divided by 50, 1.6 ampere. Current coming 1.6 ampere. P is the same. This is the useful power. Q reduced. Power factor increased. Current in the line reduced. So when we in this between the difference between this and this, so what happens when we go that way? P same, no change. Q reduced. S reduced. Power factor improved, increased. Power factor is P over S. Now it's 1. P over S, it is 0.8. Now the other thing, the line current, this is important. Reduced. So when we improve the power factor, remember this, when we improve the power factor, we reduce Q, we reduce S, we increase power factor, we reduce the line current, the current coming here. Now when we reduce the line current, this is the benefits now. We still have the same power. We're delivering the same real power, but current in the line, this line has resistance. Okay, when we reduce the current, so when the current goes, the line current goes down, we're gonna reduce the losses in the line. It's gonna go down. When losses are reduced, efficiency of the transmission higher. When the current is less, size of wire It's going to be less because let's say the current here is 200, the current here is 160. The wire you need for 160 is smaller than the wire you need for the 200. So the wire that you need when the current is smaller is less. When the wire is less, money is less. Okay, because smaller wire, less money. Now, when the wire is small, installation, when you connect the wire easier. Bigger wire is more difficult to carry, to move, to use, because in real life, those wires, they have actually even towers carry them. Okay. Another thing, when the current is smaller, you can connect another load to the same wire. Because the current is small, you can have more current. So there are lots of benefits of increasing the power factor. One of them, the main one, is to reduce the current in the line. When you reduce the current in the line, you're gonna gain so many things. So this is the topic. So when we increase the power factor, we keep the real power. We don't change it. Because if the motor needs 100 kilowatt, we'll always need the 100 kilowatt, okay, to work. So how do we reduce the power factor? By reducing S. How do we reduce S and we keep the same P? We reduce Q. Now, when we reduce Q, we reduce S, we increase the power factor, we reduce the current coming to the load. Is this okay so far? Any questions? Too early in the morning. You know the term they use here, muwasil, just doesn't sleep. This is what I do anyway. So if it's too early for you, it's actually too early for me as well. Okay, so we'll continue. We said there are lots of benefits of reducing the current, the wire size, the efficiency, the cost, the losses, okay? The ability that you can connect more loads. There are lots of good things. Now, how do we do it in real life? This is the load. It's a motor or something, machine, okay? It has P equals to, let's say 80 again, whatever, 80 kilowatt or 80. Q equals to 60. Power factor is 0.8. What we need to do, we want to improve the power factor, let's say to 1. What does that mean? We're gonna reduce Q from Q60 to 0. Power factor 1 means Q is 0. So this is the old Q equal to 60. And this is the new one. How can you reduce Q? You have to add to the system, add negative Q. What's gonna give me negative Q? Is a capacitor. So we're gonna add capacitor in parallel. This capacitor will give me negative Q. These two together will have power factor of 1. So the load is still the same, but when I add capacitor next to the load, I have the new load, the capacitor plus the load, so capacitor plus the load will have the power factor in the new one. Then the current here will be less. So for example, the current here is 2. This is gonna give me some current. The current here will be 1.6. Now the capacitor is next to the load, so it's like part of the load. This is the transmission line, the long line. that we reduce the current in here. So this is how we do power factor improvement by adding a capacitor in parallel. This capacitor is going to give me negative Q. This negative Q is going to reduce the original load Q. Once this is reduced, power factor is increased. This is the technique. Now, the procedure is not difficult. We keep in mind these things. Okay, so that Q equals V squared over XC. This is exactly like power equals voltage squared divided by R. But this is the negative Q because it comes from C. So this is the QC. Now XC equals to 1 over omega C. So we can plug it in here. So QC equals to V squared over 1 over omega C. Okay, rearrange this. So let's multiply this by that side, then that side. So QC will equal to omega. No, multiply this by there. Okay, omega C equals to V squared. If I want C, the capacitance, by rearranging this one, okay, it's gonna be capacitance there, V squared is here. So C QC divided by omega V squared. So if I want the capacitor to give me, say this is the capacitor. If I want the capacitors to give me 50 volt ampere, and the voltage across the capacitor is 10 volt. And the frequency is 50 hertz. What is this capacitor? This is the question. What capacitor should I put so it can give me 50 volt ampere reactive? You plug those values here. This is 50. This is 10 squared. This is 2 by F, which is 50, will give you C. So always the question will be, what is the capacitor that I should connect to give me this Q? This Q is a negative Q. I'm gonna use it to reduce the power factor. This might seem a little bit difficult. The last unit in Fundamental 1 is power factor improvement in single phase. For us, we're gonna do power factor improvement in 3-phase. But I still want you to understand the single phase power factor improvement, because the procedure for single phase and 3-phase is exactly the same. So this is why we're going to review single phase first before we go to the 3-phase. Okay, this is the topic. Power factor improvement. If someone asks you what is power factor improvement, say increasing the power factor. Someone says how to increase the power factor? By reducing Q. And when you reduce Q, you're gonna reduce S. And because P over S is the power factor, when you reduce this, you increase the power factor. When you reduce S, you increase the power factor. And now what is the reason why we improve the power factor? Because we're gonna gain lots of things. The main thing is we're gonna reduce the current in the system. So here's what we need to learn, what you have in here. Increasing the power factor. See, without changing the voltage or current of the original load. What does that mean? This is the load. The load voltage is 50. The load current, the current coming is 2. We're not changing those values. P is 80, Q is 60, power factor 0.8, S is 100. Okay, those they stay. We don't change this, but what we do, we add capacitor here next to the load. The capacitor was gonna give me Q negative. This Q plus this Q, they cancel out, for example, it becomes 0. So these together, the load and the capacitor, will have a power factor improved. Say power factor equals to 1. Not the load only, the load with the capacitor. The current here is the one reduced 1.6. So the load current is still the same. The load voltage is still the same. Q, P, and the load is still the same. But the load with the capacitor together, they will have a better power factor. So the power factor is improving the power factor of the system. It means the load and the capacitor together. But we're not changing anything in the load, because the load sometimes is a machine you cannot open. You're not going to say, I'm going to change it and redesign it. No, you add capacitor in parallel. That capacitor with the load together will give you better power factor. So again, increasing the power factor without changing the load. So power factor usually is adding reactive element, usually capacitor, in parallel with the load to get the power factor to be close to 1. 1 is perfect. Close to 1 sometimes is what we want. So when we improve the power factor, what do we get? We reduce the current. That reduces the power losses. That increases the efficiency. That reduces the size of the conductors. That reduces the money that you need, okay? Oh, another thing. In the transmission line, there is resistance. So there is a voltage drop here in the line. So in the current voltage drop is the current times the impedance or the resistance, okay? In the line, the transmission line. This voltage drop, when you reduce the current, the drop is gonna be reduced, and that's a good thing. If the voltage here at the sending side is 50, you don't want it to be 20 here. You want it to be close to 50. You don't want to lose the voltage and away from the generator to the load. S is gonna be less, kilovolt ampere, because Q is less. You're gonna save energy because you're saving losses, okay? Higher efficiency, you're saving the voltage drop. Now, Kahrama, I don't know if Kahrama does that or not, but other companies, like where I was, they charge you not just for P, even for Q. So if your Q is high, they're gonna charge you and you're gonna pay money because you cost them extra current. System capacity increases. It means this line, if someone takes less current, someone else can connect another load to take more current. So this line can take or can give you an extra current. So it means the capacity increases. Now details of this goes in the power system for the guys who's gonna go in electrical. But for us, we want to learn how to improve the power factor. So the line voltage is fixed. We know that. The 240 volt coming to your house, single phase, 415 line to line, voltage is fixed. Apparent power, which is S, is VI. V is constant, so V is function of S is function of I, because this is fixed. This is fixed. So when I increases, S increases. When S increases, I increases. So when S is less, this is what we said, the current will be less. And we want the current drawn is less. The minimum current happens when the power factor is 1. Q is 0. So power factor is 1. So it's good to reduce the current by reducing Q or getting close to 0. How do we do that? By adding an element, reactive element. Now if Q is positive, we add capacitor. If Q is negative, then we add inductor, because inductor is going to give me positive Q. Now here's the procedure in a single phase, and this is the stuff you did before. This is the load, inductive load. So it has P and has Q. What you're gonna do, the load is still going to be the same. It's gonna take the same current, okay? You're gonna add capacitor. It's gonna give you negative Q. So this is the original system, the load by itself. When I get negative Q, I'm gonna reduce Q, the total Q, so it will be like this. So this is the original system. When we add the capacitor, we're gonna reduce Q. That means we're gonna reduce S as well. So we're gonna reduce Q from the old one to the new one. How? The old one is 80. I want to reduce it to 20. So I have to find QC that will reduce it from 80 to 20. So QC would be 60. Okay, so it is 80. You want to reduce it to 20. We call this is Q old, before we add the capacitor. This is after we add the capacitor, Q new. The difference between them is QC, 60. So the load has 80 Q. You add the capacitor in parallel, gives you 60, but it is negative because it's QC. Total together, these together will be 20. So QC is 60, so it reduces 80 to 20. This is important. The value of QC is the difference between the old Q and the new Q. This is the procedure for single phase. So if I want to improve the power factor, this is the load. The original load has P, Q, S, power factor. Those ones are the original one. When I add capacitor in parallel, I'm gonna these two together. They will have P the same. It's not gonna be different. C is not gonna add any P or reduce it. Q, the new Q here, is less. The difference between the old Q and the new Q is QC. Q old minus Q new. So this one. QC is going to reduce the Q to the new one. Then if I want to find the capacitor that I need to connect to reduce Q from this value to this value, it's QC, this number, divided by omega V squared. the one that we just did from the analysis. And once I add the capacitor, the current here will be reduced. The current in the load is going to be the same. This current is the same as this, I1. This is going to add leading current, so we'll reduce that one. So let's say that it's like this. This is the old I1. The capacitor is going to give me a leading current, is like this. This is the current in the capacitor. So this is the new current, I2 here. It's less because capacitor gives me a leading current. Let's look at this question. Now, we don't have to follow all this. 120 volt, 60 hertz, load 4 kilowatt, lagging power factor. We want to improve the power factor to 0.95. So why is it? We have P equal to 4 kilowatt. Power factor 0.8. We want to raise it to 0.59. Now when we raise it, P, we don't change it. This is the new, this is the old. P is going to be the same, 4 kilowatt. We can find S here and S here. We can find Q here and Q here. The old, sorry, the new and the old. Now we know that S equals power factor over, P over power factor, because power factor is P over S. I have power factor and P, I want S. So S in this case is P over the power factor. I can find it here and I can find it here. Then I can find the Q. Q squared plus P squared equals to S squared. From here, if I want Q, Q equals to S squared minus P squared under square root. I find Q. This is the old Q. This is the new Q. The difference between them is QC. This is QC. I have QC. I have the voltage. I have the frequency. I can find the capacitor. So this load, which is the 4 kilowatt, this is the power factor 0.8. If we want to raise the power factor to 0.95, we're going to add capacitor. This capacitance has to be, this capacitor has to have this capacitance, 310 micro. These two together will have now a power factor of 0.95. So the load is still the same, but with the capacitor, they have less Q and higher power factor. I hope that this does make some sense, at least the sense that when we add the capacitor, we don't change the original load, but both together, the capacitor and the load will have a higher power factor. Here's an exercise here, and it's actually an example. So we have two loads together, single phase. These two loads they're supplied by this source. 200 volt, 50 hertz. This load, the first one, 80 kilowatt, 0.7 power factor. The second one, 50 kilowatt, 0.9 power factor. We want to find the total power, the total kilovolt ampere, so the total P, the total S, the power factor, both together. Then we're gonna find the capacitor that we need to raise the power factor to 1. So first, when we do those questions, we're gonna combine these two loads into one load. This is total. Okay, this is these two together as one load. How? We're gonna add P here and P here, and that is P total. If you have more than one, more than 2 or 3, you just add them. Then you find the Q total, again by adding Q1 plus Q2. Then you can find S total. It's not by adding now, no. S you don't add. If you remember what we do find P squared, the total, plus Q squared, total under square root. This is how you find S. Then you can find the total power factor, which is P total over S total. So this procedure you always need to do when you actually do power factor improvement, because you need to know what is the total load, so then you know what capacitor you need to connect. So this is load 1. Oops. This is load 1. They give me P. They give me the power factor. I can find S. Then I can find the Q for the first load. The second load, they give me B. I can find S, and I can find the Q. Now I can find the total P, which is 80 plus 50. I find the total Q, which is 80 plus 24.2. Total S is not the sum. No, don't add it because S has an angle. But P and Q, okay, P and Q, you add them normally. Once you find P total and Q total, you can find S total. So whenever you have more than one load, you're gonna combine them before you do power factor improvement. How do you combine them? For each load, you're gonna find P, Q. You add all P's together and all Q's together. Then you find S and the power factor. This is what we have here. We added P. We added the Q. We found the total S. We found the power factor. This is the old system. Before, this is one load, combined load. Now when we connect the capacitor, this combined load is basically the two loads together. I combine them into one value. So when we add the capacitor, the P doesn't change, stays the same. So the new P equals to the old P. Okay, the new power factor is given. They tell you that raise it to 1. You're gonna find S new, which is different than the S old. Find Q new, which is the same thing. It's P squared minus Q squared. Sorry, S squared minus P squared. When power factor is 1, Q is 0. Then you're going to find QC, which is the difference between Q old and Q new. Then once you find that, you can find C. You don't have to do these in two steps. You can do them in one step. C equals QC divided by omega V squared. So one more time, the procedure. If you have loads, you want to improve the power factor to those loads together. Combine them so they become one load total. When you find the total, P equals to the sum of each one. Q equals to the sum. S does not equal the sum. Don't do this. S is P squared plus Q squared under square root. The right triangle. P, S, Q, and S. Then you can find the power factor. P over S, the total here. So you find the old load, the new load. P is the same. The P doesn't change. Q new. You find it. Now, usually you would find S new using this. P divided by the new power factor, which is always given. They have to tell you, you improve the power factor to what level. Then Q is S squared minus P squared for the new now. And the new. Here S is P over power factor. Everything is in new. Then you're going to find QC. QC is going to give you the difference, reduce from old to new. So QC is the difference between the old and the new, because the capacitor is the one that is going to reduce the Q. Then the last thing, you can find C, which is QC divided by omega V squared. Here's now this question. Now what I'm gonna do the part B first, this one, just to show you the procedure of increasing the power factor, improving the power factor. So what do we have? Gonna have old, which is the load only, the motor only. New, the motor with the capacitor. This is the new. The old, before they give you the power 840. They give you the power factor 0.7. Lagging. So if it's lagging, we need the capacitor. The new here, P new. Power is going to be the same. The motor will consume the same real power. New power factor. They ask me to raise it to 1, so it's 1. The capacitor here should raise it to 1. So, steps. Now this is the first. Gonna go back. We find S old. We find S new. So the same thing. It's P over power factor. Here 840 divided by 0.7. I think that is 120 to 1200. It's not kilowatt, by the way, it's just watt. Is it 1200? Can someone do this? Get calculator and do it. Okay. Now the S new. Again, P new, power factor new. Or power factor. So 840 divided by 1 equals to 840 volt ampere. Q, old, it's S squared minus B squared under the square root. So 1200 squared minus 840. Answers 1200 minus 840 squared. $857 almost. 857 volt ampere reactive. So the same Q new, I'm gonna do the same procedure. So now it is square root of PS new minus P new. And this is gonna be 0 because these are the same and power factor is 1. So this is the first step in the analysis. Down the old system, the new system. Power, power factor, S and Q. Power, real power is the same. Power factor is given to you. S, the new is less than the old one. Q, the new is less. Now we're gonna add capacitor. Okay. Question is, what is the capacitor that we need to connect? What is the value of C here? What is it? So we have to find QC. This C is gonna reduce Q from this value. What is it? From this value to this value. So Q old minus Q new. So 857 minus 0 is gonna be 857 volt ampere. Now the last thing I need to know, what is the capacitor? It's QC divided by omega V squared. QC is 857. Omega is omega is 2 pi. Frequency is 60 given to me. and V squared is 120 squared. This gives me the capacitor C. It's gonna be something in micro maybe, or in milli. Answers. So if we change that number, Isam, with the engineering notation, it will be 157 microfarad. So this is the answer for B. This is how we improve the power factor. We look at the old stuff, the new stuff. It's exactly the same. The procedure is the same. Now I'm going to answer the A and C. So for A and for C, what is the current? So before we add the capacitor, I equals S over V. So S is, we calculate that here is 1200 divided by 120, so it's 7. No, it's 10 ampere. Now the I here is the new line, so it's a new. The voltage is still the same. So 840 divided by 120, this is the 7 ampere. So see what happens to the current. The line current is reduced from 10 to 7. So what happens before the capacitor? It was 10. After we add the capacitor, okay, this is 10 here going to the load. After we add the capacitor, the load still takes 10, but the current here is 7, because this guy gives you some current, okay, current with leading, so this current is less. The current here is still 10 because the voltage between these 2 points is the same voltage, so it doesn't change, but the current here is 7 now. These two together have a new S. Is this okay? The procedure of this is okay. Any questions? The procedure is exactly the same. Even in the 3-phase, it has one extra step only in the 3-phase, one extra step. So I'm going to continue. Here's another thing. Now a lighting load, usually lighting load has higher capacitor, but it's okay. So here's what we have. We have a load. This load has this power factor. They want what capacitor they should connect to increase the power factor to 0.9. Now lagging, it means we connect capacitor. So where is it? So again, so what I'm gonna do, the old system, the new system. Now the old, it means just the load by itself. The new, it means when we add the capacitor. You can see now the procedure is exactly the same. Few details, just the difference between question and another question. They give you the P here, the old, okay, which is 1 kilowatt. They give you the power factor, which is 0.707 lagging. Now the new power factor, they give you the new power factor. They want it to be 0.9. We know the P new, the new doesn't change. P doesn't change. Capacitor is not gonna add anything to the real power. We're gonna find S old, S new, Q old, and Q new. The procedure is the same. So P over the power factor. So this gives me 1000 divided by 0.707. So this is gonna give me 1414 volt ampere. Q alt P squared, S squared minus P squared. Always remember, P is the real, Q is imaginary, S is the hypotenuse. So the relationship is S squared equals to P squared plus Q squared. So if I want Q, I'm gonna move this to the other side, becomes negative, and I take the square root. So this is 1414 squared minus 1000 squared under the square root. This gives me 1000 volt ampere reactive. Here's the same thing, P new over power factor new. So it's 1000 divided by 0.9. This gives me 1111 volt ampere. Then P is S new squared minus P new squared, which is the same. P doesn't change. So this is 1111 squared minus 1000 squared. This is gonna give me a number. Can you guys give me the answer? Okay, one second. Try this. Give me the answer. Okay, 484. That's what I got from you guys. Thanks for that. I'm gonna just write it here. 484 volt ampere reactive. So the last thing that when we add the capacitor, it's gonna reduce Q from this to this. So QC is actually Q old minus Q new. So this gives me 1000 minus 484. That gives me 516 volt ampere reactive. The last thing, you want the size of the capacitance. So the capacitance C is actually QC divided by omega V squared. So Q is 516 divided by the voltage is given 2 by the frequency is 60. I don't know why I'm using frequency 60. Frequency here is 50, where I'm still using the Canadian frequency. In my mind is always the frequency 60. Why is it 208 squared? So whatever you get is your capacitor, and this is the answer for this question. Okay, again, the procedure is the same, and now I'm gonna tell you what is the difference between single phase and three phase, and what is the difference between more than one load or one load. Just give me the answer for this, please. So 31.6 microfarad. Now, so this is when you have one load single phase. How is it gonna be if you have more than one load? Okay. So if you have more than one load, you're gonna combine them here into one load. So if you have more than one load, if you have loads, like instead of one, you have more connected here. So you combine them, you're gonna find P total and Q total. It's the sum of the all P's and the sum of the all Q's. Then once you have the total, do the QC and C. If you have three phase, it's the same procedure until here. If you have three phase, QC, you're gonna find it per phase. So it's QC over 3. And voltage, you're gonna find it V phase. Because the capacitor is in one phase. Every phase will has one capacitor. So it's like Ohm's law here applied, this capacitor per phase. So you have to do QC per phase. So this is per phase, and this is per phase. This is the difference. But all this is the same. This is the same for 3-phase, single phase. Until you reach QC. Once you reach QC, after this step, you're gonna say, okay, when I plug in the last equation to find C, I have to make sure this is per phase, this is per phase. Now here's the 3-phase connection here. How many loads? We have 2 loads. The answer is here, by the way. Then we have 3-phase, 2 loads, and this is the end of this lecture. So, the same thing. First, when we have more than one load, we're gonna combine them. Okay, we're gonna combine the loads. What does that mean? We're gonna find the total P and the total Q. Then, what we're gonna do, we're gonna look at the old system and the new system. We're gonna find Q new and Q old, which is basically this Q. The difference between them give me QC. Then the last step, when I find the capacitor, is the last step, which is QC over omega V. Okay, I have to make sure, because it's capacitor per phase, I have to make sure that QC is phase and V is phase. That's it. So the last step is the difference. Okay, here's we have 2 loads. This is this one, the load 1, 30 kilowatt. Power factor is 0.6. The second load, this is 45 kilovolt ampere reactive, and power factor is 0.8. So I'm gonna find total P and total Q. This is the first thing. Then I start the old and the new. Says find the total, determine the complex real reactive power observed by combined load when you combine them. So this is an extra question that will help me in this. Then they say find the kilovolt ampere rating for the 3 capacitors connected in delta. So they only find the QC. You don't want to find, I want you to try to find for each load, I want you to try to find P and Q. Actually, the answer is in the next page. So, okay, so for the first load, they give you this, and they give you the power factor. So you can find S, you can find the Q. By the way, here's another way to find the Q, by finding the angle. So theta is cosine inverse of the power factor. So you can find the angle. You know, power factor is cosine the angle, right? You can find the angle. Once you find the angle, which is in this case is, I think, 36.9, you can find S, which is P over power factor. You can find the Q by another way, which is S sine the angle. So this is another way to do it. Or you can just say it is S squared minus P squared. Either one of them is fine. So here they used the angle. Sine of the angle is 0.8. Here they used the angle as well. They find cosine the angle power factor is given is this. So you can find the other one. S is a Q over sine the angle, because S sine the angle gives you Q. P is S cosine the angle, remember that. So you can find P by S cosine the angle, which is, there is an equal sign here. So once you have P for each load, 30 here and 60 here, Q for each load, 45 here and 40 here, you can combine them. So 30 plus 60 is 90, 45 plus 40 is 85. Now once you have one combined load, you can do the second part of the question. The second part of the question, important to read it. It doesn't say find the capacitor, it says find QC. Okay, it's find QC. The kilovolt ampere rating is the QC. It's not the capacitance of the capacitor. Oh, here's find the capacitance as well. Yeah. So, and the capacitance after. Okay, so both. So we have the old system, 90 kilowatt, 85 kilovolt ampere reactive. This is the Q, this is P, this is a Q. Okay. The new system, P is the same. Power factor, the new is 0.9. So I can find S. And I can find the Q new. This is a way to find it. S sine the angle, or S squared minus P squared under the square root. Then you find QC. This is for the three phase. Okay, this is for the three phase. So if you want single phase, now remember at the end we said we use one phase. So we take the three phase Q divided by 3. Gives you this number. Then we use the phase voltage. They give me the line voltage. Okay, in the question, 240 kilovolt. This is to give me the line voltage. But the capacitors are connected delta. So when the capacitors are connected delta, V phase equals V line. They plug them here. Now the same exercise we're gonna do it here. Okay, we're gonna do the same exercise here. So the example for you to do, this is just an exercise that we want to do together. Okay, so if it says calculate the real power, total real power, total reactive power, total complex power, and the power factor. We need to calculate these ones anyway for the part P, which it says find the per phase capacitance. 3 capacitors are connected Y now. What does that mean? 3 capacitors are we're gonna add 3 capacitors, and the 3 capacitors are connected Y. This is the Y connection for the capacitors. This is Y connection, 3 capacitors. Each one of them is C. Now, if the question says connect them delta, this is how they will look like. So this goes to one line, this goes to another line, and this goes to a third line. This is 3 capacitor connected delta. Now, there is another way to connect the capacitors in delta. If you look, I'm gonna just make it bigger here. You can connect the capacitors like this. This is delta connection here. The reason, look at this capacitor. This capacitor is connected between A and B. So this is the capacitor between A and B. This capacitor is connected between A and C. So this is this capacitor. This one here is between B and C. Between B and C. So this is this capacitor. So this is delta connection as well. Now V line equals V phase for delta. V line equals square root of 3 V phase for Y. Line voltage, this is the capacitance. So this connection is actually the delta connection. Now if we want Y, this time the capacitors are connected in Y. So they're like this. Connect them in Y. That's Y connection here. Or it's the same as I said. Just like this. This is Y connection. Now because it's Y connection, this is what we have. The phase voltage that we're going to use at the end is V line divided by square root of 3. So how do we do this? The first thing, we're going to combine the loads. So this is load 1, load 2, then the total load. Then we're going to actually have the new values, because this is the old. So the load 1, 700 change the color. Okay, so load 1, S is given 700 kilovolt ampere. Power factor for the load 1 is 0.8 lagging. Now we can find P1, which is S times the power factor. S cosine. So this is 700 times 0.8. That gives me 560 kilowatt. Then I can find Q. I can use whatever technique. Now the easiest for me will be S1 squared minus P1 squared under square root. So this is 700 squared minus 560 squared under square root, and that should be 0.420 kilovolt ampere reactive. So this is the first load. We found P, S, and Q. Is this okay for the first load? Quite. The second one. We have the second one. They give me the kilowatt, so I know P here. P2 equal to 800 kilowatt. They give me the power factor 2, which is 0.9 lagging. Lagging means the Q is positive. Then I can find S2, which is P2 over the power factor. So it's 800 divided by 0.9, and that gives me 888.8 kilovolt ampere. Then I can find the Q, which is S2 squared minus P2 squared under the square root. This is any answers here? 888.8 or 0.9 actually, because you round it up, squared minus 800 squared under the square root. Kilovolt ampere reactive is the value here. 3, let's say 88. Okay, just round up. Okay. So this is load 1, load 2. This is before we actually combine them. Then we find P total. Is this plus that one. So 700, 800 plus P1 plus P2. So this gives me 560 plus 800. This is 1360 kilowatt. Q total is this plus that. So this gives me Q1 plus Q2. When we plug in 420 plus 388, this gives me so 800 kilovolt ampere reactive. And I can find S total, which is P squared total plus Q squared total. Then I can find S here. What else to say? Their total reactive, total complex power. Complex power S is actually P plus JQ. So that is 1360 plus J 808 kilovolt ampere. Power factor is P over S, apparent power, and whatever is going to be lagging. Anyone that can give me the answer for here? 1360 squared. 1360 squared plus 808 squared under square root. Give me the answer, please. One, 5, 8. Let's say 2 kilovolt ampere. So this is 136 divided by 1582. You can get the answer. Now, now the new and the old. This is the old. The total is the old. Calculate. We want the new power factor. New power factor is 1. P new is the same as the old. 1360 kilowatt. Q new, before that let me just do S new as P new divided by power factor new. Now divide by 1360 kilovolt ampere. Q new is P new S new squared minus P new squared. It's gonna be 0 because they're the same. Power factor is 1, so it's 0. So from here we can find QC, which is Q old minus Q new. Q old is 808. The total here, the total minus 0, so it's 808 kilovolt ampere reactive. Now up to here it's the same as single phase, or three phase is the same. Now what is the difference is because this is three phase, we're gonna find the QC per phase, which is 808 divided by 3. So this is gonna be what is gonna be? So a 60, 600 is 200, 150 is 250, 270. So it is 269.3, I think, kilovolt ampere reactive. Then we're gonna find V phase. Now Y connection, V phase equals V line divided by square root of 3. V line is given 13,800 because it's in kilo, divided by square root of 3. So this is the difference. We're gonna do phase and phase. Then the capacitor is the last thing, is the same thing. So it's QC per phase divided by omega V phase squared. So it's 269.3 times 3 to the power 10 to the power 3 because it's in kilo, divided by frequency is not given, so it's 50. 2 by frequency is 50, and the voltage, whatever this gives us, 13,800 divided by square root of 3. I think that is 7,977 volt. So 7,977 squared, and this is the final answer. So the difficulties would be in combining loads, but once you have one load, it's not difficult to in new values, old values. Once you get QC, if it's single phase, you use it right away. If it's a 3-phase, you're gonna find QC per phase and voltage per phase, and you plug them in. Is this okay? We're gonna stop here. We're going to stop here because next class I want to review this one more time. Might be difficult, so next class, which is gonna be on Thursday for you guys. Okay, so we're gonna review this next class again. Let me take the attendance, the amazing attendance today. I think I only have a few people. So okay, I got the attendance from the list, so you guys are good to go. We only have a few things left in this.